Okay, it's time for Module 2 for Week 9. And we're looking at something called the May model. And this is kind of concluding our look at populations and what happens when we put the rabbits on that island. Okay, so in the last module, we looked at the Lotka-Volterra equations. And we saw there were two kind of like different flavors. There was with logistic growth or without logistic growth. And so when we had logistic growth, we didn't have periodic behavior. It kind of settled out eventually to some sort of stable population. And if there was no logistic growth, then we had this nice periodic behavior. Okay, now, so you can complain about this, right? Because at the start, when I started talking about population, I was all saying how great logistic growth is, that that's the best thing, it's the most realistic, so we expect to see logistic growth. Okay, so we definitely want logistic growth in our model. The problem is that that's not what we see in nature. So take a look at this slide here. So there you see a Canadian lynx chasing after a snowshoe hare in the snow. And we have lots of good data about these populations. If you look at the graph there, going back to 1845, you might think, what's that all about? Well, if you look, it's the number of pelts gathered by the Hudson Bay Company. Okay, and so that is that is going to be some kind of fraction of the actual population of hares and lynxes. It might not be the same proportion of hares and lynxes because, you know, you might put more effort into catching lynxes because the fur might be worth more or whatever. But again, you see nice periodic behavior with the hares peaking before the prey, peaking before the predator. Okay, so we want our models to have logistic growth and periodic behavior. So we have to do something about that. And we can do that because the model, the Lotka-Volterra model, was very basic. It was just like first assumptions. So let's try and do something better. Okay, so we need an Australian. So we're proud of this guy. He's Robert May. He's a famous Australian scientist, although he did most of his work at Oxford University, and he was also at Princeton and Harvard. So he was a big guy in biology. He actually became Baron May of Oxford. He was put in the House of Lords. That's because he was, for a while, he was the chief science officer for the UK, and he was also president of the Royal Society, so he was a bigwig. His book on epidemiology is kind of like a standard text in the field, and he's famous for taking mathematical techniques and applying them to ecology, to biodiversity, to epidemiology, all kinds of interesting things where you kind of want to know what's happening. Okay, so here's the model. So what assumptions does he make? Well, first off, he wants logistic growth. So without foxes, the rabbits grow logistically. We shouldn't even talk about the foxes without rabbits, right? Because predators need prey. If there's no prey, there's no predators. So we want the foxes also to grow logistically in the presence of rabbits. And in fact, we want the carrying capacity somehow to depend upon the rabbit population. Now, there was a second point of the Lotka-Volterra model that May had problems with. And if you think about it, it's quite silly. And that was the assumption that each fox ate a fixed proportion of the number of rabbits there are. So that means, you know, like if one day the fox is eating 2 rabbits a day and suddenly the rabbits increases tenfold, population increases tenfold, then it's going to eat 20 rabbits a day. And then if it increases 10 times again, it's going to eat 200 rabbits a day, etc., etc. You know, and eventually it's going to eat, 10 billion rabbits per day. And that's not how appetite eating works, right? So at some point, the fox is going to have enough food for the day and it's not going to go out and hunt anymore. Okay, so we want the number of rabbits eaten to depend upon the population of the rabbit, but we want some saturation point to be reached. Okay, so that which it doesn't go beyond. Okay, let's turn that into formulas now. So if we're going to let D be the rate at which a single fox eats rabbits, and let S be that saturation rate. That's the if a fox could have as many rabbits as it wanted, that is going to be S. That's going to be the rate at which it's going to eat those rabbits. And so we model D by this fraction, SR divided by R plus D, but really you should think about it as S, the maximum rate, times R divided by R plus D. Now R divided by R plus D is just a proper fraction. It's going to be between 0 and 1. So when R is 0, that's going to be 0. And as R goes to infinity, R divided by R plus D goes to 1. And so that means the maximum rate is going to go to S. Okay. So that gives as the model for rabbits then that R prime is a logistic term, KR times 1 minus R divided by C, minus a predation term, which is S times RF divided by R plus D. And so your first question for the module, so this is not a homework question, which is due next week. This is going to be due Friday. Why do we multiply D by F? Okay, so there should just be a simple one sentence answer to that. And the model for foxes is the logistic model, KF times 1 minus F divided by CR. Hang on, what's the CR? And so that's your second question. Explain why we have C sub F times R in the denominator as the carrying capacity. Okay, so you notice that for the parameters K and C, the growth rate and the carrying capacity, I'm using subscripts, sub R and sub for rabbits and sub F for foxes. Okay, so of course I've got an Excel file for this model, and so this is the one that I implemented. Again, I just came up with some parameter values to put in. Okay, and so we go ahead and we run that model, and on the next side is the graph that we get for this model. And oh, that's nice and successful. It kind of looks a little bit more like what we saw for the hares and the lynxes. Okay, the hares and lynxes, of course, they had much more kind of random factors put in, but this looks like pretty good. Okay, it's logistic and it's periodic. Okay, so you might ask, well, hang on, aren't the rabbit numbers a bit low? Well, what I did is I let R be the number of centirabbits, that is a group of 100 rabbits. So instead of multiplying the number of foxes by 100, I divided the number of rabbits by 100. Okay, so as I said before, we are seeing periodic behavior, and we see that the peak that the top of those peaks is around 780 rabbits, and for the foxes it peaks a little bit above 5, and we're seeing a period of around 40 months. Okay, great. Okay, so what I did on the next few slides is I changed the initial conditions, and I wanted to see what happened. So the next graph here, I've got 2,000 rabbits and 20 foxes. So remember, the 2,000 I divide by 100, so I get 20 centi-rabbits and 20 foxes. And oh, believe it or not, we still have a period of 40 months. The peak rabbit population is around 7,800, and the peak fox population is a little bit above 5. Okay, and so then if I look at 1,000 foxes, 1,000 rabbits and 10 foxes, we get this, and it looks different from before, but it really isn't, because we've changed the scaling. And so we see that, again, a period of around 40 months. Again, the peak rabbit population is around 7,800, and the peak fox population is a little bit over 5. And then finally here we've got 1,000 rabbits and 20 foxes, and we see the same thing. A period of 40 months, a little bit over 780 rabbits, and a little bit over 5 foxes. Okay, so this is looking pretty good. And that sort of changes another thing that was different from the last model. So if you remember, in the last model, the different starting conditions led to different kind of periodic behavior. And that's another thing that an ecologist or a biologist might quibble with, saying that, well, the long-term behavior, it shouldn't depend upon how you start. In the end, you should settle down in some behavior, kind of like with the logistic equation, we saw that it settles in on the carrying capacity. Here we're seeing it settle in on some kind of periodic behavior. And so if you try and do the same thing that you did, that you're doing for your homework, the homework question, remember, for the Lotka-Volterra, is to try and find stable populations. If you try and find stable populations for this model with these parameter values, you're not going to be able to find them. The homework question for this one is to change the parameter values a little bit, and then you'll see that that kind of stable population is possible, just where there's no periodic behavior, it just sort of settles in on stable equilibrium. Okay, so this is a pretty good model. So it has logistic growth, it has periodic behavior, and it also has stable behavior. So it kind of has like a rich variety and of behavior, and it seems more realistic. Okay, so that is it. Hang on, and talk to you later.